Hi all, I am Divya James, Assistant Professor from Rajagiri School of Engineering and Technology, and in this lecture I will be covering the Module 3 Design Communication of the subject EST200 Design and Engineering. The topics covered under this module includes importance of communication in design, communicating designs graphically, communicating designs in writing, communicating designs orally, prototyping, proof of concept, and mathematical modeling in design. So the designers and engineers usually solve the problems and they try to address the needs of people by designing the products and solutions. The success of design depends on how effectively they can present the problems and their ideas and solutions while they interact with various levels of customers during the design process. And in this module, Design Communication, we'll be discussing the various modes of communication the designer can use while interacting with his or her customers during the design process. So moving over to the topic 1, the importance of communication. As you all know, the primary aim of a designer while designing a product is to satisfy the needs of his or her customers. And the customers of a designer can include end users, sponsoring organizations, manufacturers, sales operators, service or maintenance people, and it carries on like that. And hence the designer should be able to communicate clearly and effectively with the people of different background and skills in different ways, and some of the ways can be either through orally, or it can be either through sketches or drawings, or it can be through writings. The designs might fail to satisfy the needs of the people and the designs might not be accepted if the communication is not effective. For example, the conceptual design drawings can be used by the customers and detailed design drawings with dimensions, tolerances and material selections and bill of materials for manufacturers. So this is a popular cartoon which shows the failure of design due to lack of proper communication. So these are the different ways by which the designers communicate with their customers. It can be either through freehand drawings, sketches, illustrations, figures, graphics or diagrams. It can be also through 2D or 3D diagrams. It can be through writings or written design reports, oral presentations, mathematical models, prototypes and proof of concepts. Communicating designs graphically. So communicating designs graphically includes the usage of visuals such as figures, diagrams, charts, graphs, 2D and 3D drawings. Visuals are used to explain, illustrate, demonstrate, or verify or support the textual material in the written design reports. What cannot be expressed orally or in writing can be well communicated through visuals. A designer starts off with a freehand drawing and sketches, which are then done in CAD as 2D or 3D drawings. 2D drawings usually provide more details which is required for manufacturing the object or the part in a shop floor, whereas 3D drawings and virtual reality helps the designers to visualize the object. So visuals are only valuable if their presentation is effective. So there are some guidelines to be followed while preparing the visuals. The general guidelines for preparing the effective visuals are: reference all visuals in the textual report, reference the source of data or figure if it is obtained from other documents or web, carefully plan the placement of visuals, specify all units of measure and the scale used in the drawing, label each illustration with an identifying caption and title. Spell out the words rather than using abbreviations. Include a list of figures at the beginning of the report if it has 5 or more figures. Avoid putting too much data in an illustration. The example below shows a bad illustration where the labeling is missing and the scaling is not proper for an efficient display of the curve. Given below is a better example of the same illustration where the labeling and units are clear, scale is proper, and the grid lines makes it easy to look at the graph closely. The detailed design drawing should have the following essential components: standard drawing views, standard symbols to indicate the particular items, clear lettering, clear and steady lines, dimensions and units, permissible variations or tolerances, appropriate notes including the specification of materials, a title for the drawing, designer's initials and date it was drawn. Given below are the few examples of design communication using sketches, drawings, and diagrams. Communicating designs in writing. A formal technical design report is usually written at the end of a design project. Generally, it is a complete standalone document written for people who have widely diverse backgrounds. The outline of a typical design report contains a cover page, which consists of title of the report, name of the author, organization name and address. Next, it should contain a summary, which should be standalone, and it should summarize the work and also should include a short conclusion. Next, it should have a table of contents. The details of the figures and tables are put under the list of figures and list of tables. The design report should also describe the system or situation under the investigation. It should also provide a brief statement of the specific problems to be solved and summarize the needs of potential clients or users in terms of corresponding goals. So all this background work is put under the introduction. The design report also contains design process section where the details of the procedure followed in the design process is explained, and it has got an alternative solutions or concepts developed section which should summarize each of the alternative solutions that were developed. Also, it should provide sufficient detail so that the reader will be able to understand the composition of each design together with its functioning. The design report should also have a final design solution section which may be divided into several subsections, and it shall include the following details: summary of the evaluation and comparison of alternative solutions that led to a choice of final design, the strength and weakness of the final design solution. The final design solution section should also include the technical analysis and design details, which includes the conceptual design sketches, detailed design drawings and diagrams, details of the construction of the artifact, the equipment and tools used, assembly and setup procedures, experimental setups and results, details of final results, economic evaluations of the design, and feedback tables summarizing the reactions of various groups such as potential users, manufacturing personnel, marketing executives, and financial analysts. The design report should also include the conclusion and recommendation section, where the conclusion section concisely states the conclusions that can be drawn from the work, and the recommendation section suggests further work or improvements that should be performed on design, development, and implementation. Finally, the design report should contain the reference section, which lists all the documents to which the writers are referred, and the appendices, which should include the material deemed beyond the scope of the main body of the report, such as additional technical data, journal articles, patent information, marketing studies, correspondences, etc. The appendix section may be divided into as many subsections as necessary. The 5 operations involved in writing a high-quality report includes planning, outlining, writing, editing, and rewriting. These operations can be best remembered with the acronym POWER, where P stands for planned writing, O stands for outlining the report, W stands for writing, E stands for editing, and R stands for rewriting the report. Some of the attributes of good writing are: write objectively as possible, do not become emotionally involved or attached to a problem or a solution, be reasonably methodical, record whatever is learned and whatever work is performed. Always strive for clarity in writing and keep it simple and straightforward. Deliver the written material on time. Some of the attributes of good reports are: delivered on the due date, effectively answer readers' questions as they arise, give a good first impression, read coherently, contain an effective summary and conclusion, write clearly and concisely, and provide all pertinent information. Now let's see some of the mechanics of writing which will help you to avoid some of the most common mistakes in your writing. Paragraph structure. Each and every paragraph should begin with a topic sentence that provides an overall understanding of the paragraph. Each paragraph should have a single theme or conclusion, and the topic sentence states that theme or conclusion. Sentence length. The sentences should be kept as short as possible so that their structure is simple and readable. Long sentences become complex, prone to grammatical errors, take considerable writing time, and slow the reader. Pronouns. Avoid the use of pronouns like it, this, that, and so on, where it would be better to use one of the several nouns. It may be clear to the writer, but it is often ambiguous to the reader. In general, the personal pronouns such as I, you, he, she, mine, our, us, etc. are not used in reports. Spelling and punctuation. Errors in these basic elements of writing are inexcusable in the final draft of the report. Tense. Use the following rules when choosing the verb tense. Past tense, which is used to describe work done when you were building or designing, or in general when referring to past events. Use the present tense in reference to items and ideas in the report itself. Use future tense in making predictions from the data or results that will be applicable in the future. Communicating designs orally. The main method of oral communication is presentation or speech. The designers or engineers should be able to sell their ideas by effectively presenting their designs to other people. Every presentation should have an objective which may vary from one presentation to another. The presenter should be aware about the audience and their education or skill level and customize the presentation accordingly. Use appropriate tools such as slides, models, transparencies, audio-visual aids, and the web. Keep the presentation within the time allotted. People resist the change as humans like familiar method, and change requires additional effort. Typical reactions of people to change include: we tried before, it's a too radical change, we have never done that before, get back to reality, we have always done in this way, I don't like the idea. So only 7% of the communication happens through spoken words. Remaining 93% happens through non-verbal means, such as 38% through voice inflections and 55% through facial expressions and body language. Now let us study some of the do's and don'ts in oral presentation. So when you're making an oral presentation, know your audience thoroughly. Never read slowly from slides and notes. Catch the attention of the audience in the first few minutes. Stay within the time allotted. Include all relevant examples, stories or jokes. Avoid using technical jargons which audience may not know. Know your stuff, prepare well. Practice, practice and practice. Speak confidently but not aggressively. Maintain eye contact with the audience members and keep shifting that contact to the talk. Never talk to the board or to empty space. Present the material in a logical order. A logical presentation is much more critical in an oral one than it is in a written one. Be genuinely sincere and professional. In order to make your oral presentation as effective as possible, consider the following points. Use visual aids such as sketches, graphs, drawing tools, photos in order to convey your information more effectively and efficiently. Limit the slides to not more than one per minute. Each slide should contain one idea, and the first slide should show the title of your presentation and the names of the collaborators. The second slide should give a brief outline of the presentation, and the last slide should summarize the message you just delivered. If you need to show a slide more than once, use a second copy. Avoid leaving a slide on the screen if you have finished discussion on the topic. Never read directly from the slide. Use graphs to explain the trends or variations. Begin with the presentation of the problem, followed by the design process, solutions, and conclusions and recommendations. Finish ahead of schedule and be prepared for the question answer section. For the question answer session, allow the audience to complete the question before answering. Avoid being argumentative. Do not let the questioner feel that the question is stupid. Adjourn the meeting if the questions slack off. Thank the audience one final time after the question answer session. Now let's see the next topic, prototypes, models and proof of concept. So what are prototypes? Prototypes are working models of design artifacts. They are first full-scale and usually functional forms of a new type or design of a construction. So they are the original models on which the something is patterned. A model is a miniature representation of something, or it can be a pattern of something to be made, or it's an example for imitation or emulation. Models are used to represent some devices or process. It could be, for example, paper models or computer models or physical models. The models are usually smaller and they are made of different materials than the original artifacts they represent, and they are typically tested in a laboratory or in some other controlled environment to validate their expected behavior. So what's the difference between prototypes and models? Prototypes are intended to demonstrate that a product will function as designed, so they are tested in their actual operating environments or in similar uncontrolled environments that are very close to the relevant real world as possible. For example, an aeroplane prototype is made of the same materials and has the same size, shape and configuration as those intended to fly. Models are intentionally tested in controlled environments that allow the model builder to understand the particular behavior or phenomenon that is being modeled. For example, a model aeroplane would likely be much smaller. It might be flown in a wind tunnel or for a sheer enjoyment. The decision to build a prototype depends on the size and type of the design space, the cost of building a prototype, the ease of building the prototype, the role that a full-size prototype might play in ensuring the widespread acceptance of a new design, and the number of copies of the final artifact that are expected to be made or built. Try to ask these questions before designing to build a prototype or model. What do we want to learn from the model or prototype? Who is going to make it? Do we have the expertise to build it in-house? What parts or components can be bought, how and from what is it going to be made, how much will it cost. True prototypes are typically made from the same materials that are intended for the final design. Of course, those materials may change for the final design as a response of what was learned from the prototype. A model, on the other hand, can be constructed from whatever material will assist in answering the questions for which the model was designed to pose. The most common materials for model construction are paper, cardboard, wood, plywood, polymers, aluminium, and mild steel. There are many options for constructing prototypes and models. Mockups. One option for making basic models or prototypes is to construct a mockup of a 3D part from 2D cutouts. These 2D parts can be made using a vinyl cutter or a laser cutter, and the parts are then assembled into 3D mockups of a design. The materials used for these mockups might be foam, thin plastic, or wood. We may have the option of making the parts or all of our prototypes ourselves in a workshop or a machine shop. Typically, there are separate machine shops for woodworking and metalworking. Woodworking machines include drill presses for making holes, bandsaws for cutting at various angles, and lathes for reducing the diameter and creating the parts with symmetric curved surfaces. A metal shop includes lathes for reducing the diameter of a part, tapping a hole for facing the end, and mills for creating the slots, holes, and flat surfaces. A fab lab or workshop with CNC machines or laser cutting machines, cast metal molds, injection molding, etc. are examples for these. Rapid prototyping is a general term encompassing techniques which is used to create 3D physical models directly from electronic data such as CAD files. There are certain wireframing or screen mockup tools such as Figma, Balsamic, Fluid UI, Lumsy for software prototyping. There are certain software design or modeling tools like StarUML, Rational Software Architect for modeling or design of softwares. In the next few slides, you can see examples for models or prototypes. A proof of concept refers to a model of some part of a design that is used specifically to test whether a particular concept will actually work as proposed. In proof of concept testing, controlled experiments are designed and executed to prove or disprove a concept based on the outcome. It's an exercise in which the work is focused on determining whether an idea can be turned into a reality. In software development, for example, a proof of concept would show whether an idea is feasible from a technology standpoint. For startups, a proof of concept would demonstrate the financial viability. A proof of concept plan would address how the proposed product or service will support the organizational goals, objectives, or other business requirements. Thus, a proof of concept process should include a clearly defined criteria for success, documentation for how the proof of concept will be carried out, an evaluation component, and a proposal for how to move forward for the POC to be successful. Moving to the last topic of mathematical modeling in design. As you all know, mathematics and physics are very much part of the design process. Our designs are based on the basic principles and concepts in mathematics and physics. Mathematical models helps the designers to predict the behavior of the systems or devices that they are designing. We can represent the behavior and function of real devices in mathematical terms. For example, every new airplane or building represents a model-based prediction that the plane will fly or the building will stand without producing unintended or tragic consequences. So mathematical modeling is an activity with underlying principles, methods and tools. These principles, methods and tools helps to address certain questions during the modeling process. The questions are: why do we need a model? What will we use the model for? What do we want to find with this model? What data is available? What can we assume? How should we develop this model? That is, what are the appropriate physical principles we need to apply? What will our model predict? Can we verify the model's predictions? Are the predictions valid? Can we improve the model? So, the mathematical modeling or the principles will address these areas during the modeling process. So, the basic principles of mathematical modeling depends on three elements: abstractions, scaling, and lumped elements. Abstraction is nothing but it's about choosing the right level of detail for the model. It depends on the purpose and intended use of the model. It leads to identifying the right scale for our model. Scaling is deciding about the magnitude or size of the model with respect to physical dimension of the device or the object being designed. A lumped element model is a model in which the actual properties of a real object or device are aggregated or lumped into less detailed or more abstract expressions. When we lump into our lumped elements, depends on the scale on which we choose to model, which depends in turn on our intentions for that model. In the following slides, you can see the explanation for these basic principles when you model an airplane in many different ways depending on your goals. So now that we have seen the basic principles of mathematical modeling, there are also certain mathematical tools that we can use to apply the principles like abstraction and scaling to develop, use, verify, and validate the mathematical models. These tools include dimensional analysis, physical idealizations and mathematical approximations, linearity, and conservation and balance laws. The basic method of dimensional analysis involves the following steps. List all the variables and parameters of a problem and their dimensions. Anticipate how each variable qualitatively affects the quantities of interest. That is, does an increase in variable cause a decrease or increase? Identify one variable depending on the remaining variables and parameters. Express that dependence in a functional equation. Choose and then eliminate one of the primary dimensions to obtain a revised functional equation. Repeat step number 5 until a revised dimensional functional equation is found. Review the final dimensional functional equation to see whether the apparent behavior accords with the behavior anticipated in step number 2. We generally idealize or approximate the situations or objects so that we can model them and apply those models to find the behaviors of interest. The sequence of steps are given below. Identify the elements that are important to the problem. Translate the physical idealizations into a mathematical model. For example, consider the geometrically similar objects, that is, the objects whose basic geometry is essentially the same. Say two right circular cylinders of radius r and respective heights h1 and h2. The volume or the total volume of two cylinders is represented using the formula pi r square h1 plus pi r square h2, which is equal to pi r square into h1 plus h2. This equation demonstrates that the volume is linearly proportional to the height of the fluid in the two cylinders. Many of the mathematical models used in engineering design are statements that some property of an object or system is being conserved. For example, the motion of a body moving on an ideal frictionless path might be analyzed by stipulating that its energy is conserved, that is, energy is neither created nor destroyed. Sometimes, as in modeling the population of an animal colony or the volume of a river flow, quantities that cross by a defined boundary must be balanced. That is, we have to count or measure both what goes into and what comes out of the boundary of the domain we are watching. Such balance or conservation principles are applied to assess the effect of maintaining levels of physical attributes. Thus, conservation and balance equations are related. That is, the conservation laws are special cases of balance laws. These are the reference books for Module 3, Design Communication. Thank you so much for watching the session.